Welcome to the first in this series of videos dedicated to electrical system operation and diagnosis. When we think about automotive electrical systems, most of us know that the battery is one source of voltage for the vehicle's electrical systems. In addition, most of us know that the alternator supplies voltage to recharge the battery and supply voltage when the vehicle is running. However, most of us don't really understand what electricity is or how electricity works, and we don't know how to read wiring diagrams that can help a technician troubleshoot the electrical systems. After viewing this video, you should be able to identify the components used in automotive circuits, describe the basics of electrical principles, explain how electrical circuits and their components operate, and describe the concept of voltage drop. Electricity is a naturally occurring phenomenon that results from the movement of electrons from an area where there is a surplus of electrons to an area where there is a relative lack of electrons. Electrons are a part of the basic element of matter, the atom. An atom is made up of a core or nucleus that has positively charged protons and neutrally charged neutrons. The negatively charged electrons orbit the nucleus in layers of rings called shells. Balanced atoms have an equal number of protons and electrons. The electrons of the outer shell and conductive materials can be made to move to atoms with a more positive charge when a force is applied to them. These electrons are called free electrons. As the free electrons leave the outer shell of one atom for another, that atom becomes unbalanced or positively charged. This positive charge creates a potential that attracts electrons to move through a conductor. Voltage is the measure of the difference in potential between an area with an excess of free electrons and an area with a lack of free electrons. Because the voltage potential causes the electrons to flow along a path, voltage is often referred to as electromotive force. The rate at which the electrons flow is called current. Current can be measured in amperes, which is a count of the number of electrons that pass a given point in 1 second. The path that the current flows through in automotive systems is a circuit. For current to flow, the path must be a good conductor. Good conductors, such as copper, silver, and gold, have one electron on the outer shell that can be easily moved through electromotive force. Moreover, for current to flow, the path or circuit must be complete, from the area of high positive potential to the area with less positive potential or negative side of the circuit. As current flows through a circuit, it encounters resistance that opposes the free flow of electrons. Resistance can be in the form of the air between the atoms. It can be a change from a larger path to a smaller one, or it can be in the form of a load in the circuit that consumes voltage. A potential must be present to cause current to flow. In an automotive system, the pressure comes from the battery, which produces a constantly positive or direct current by a chemical reaction. Potential can also be produced by the alternator that generates a current that alternates between positive and negative and back to positive. To be usable in an automotive system, the alternating current is converted to direct current. To understand electricity, it helps to think in terms of something you can visualize. In simple terms, this train set is like an automotive circuit. Electricity can only flow in a continuous loop, much like these train cars going around this track. To make this analogy easy to understand, let's look at how this train set is similar to a circuit from the wiring diagram. At the top left of the wiring diagram, we have a battery. Moving left to right, we have a fuse, and a switch, and a load or light bulb, and a ground point back to the battery. Our track is the conductor, hooking everything together. Let's see how this circuit actually works. It all starts at the battery. The battery produces voltage through a chemical reaction. Voltage is the pressure that pushes electricity through a complete circuit. If we look inside our battery, we can see the freight cars being filled with voltage and pushed out through the positive side. After the voltage is used up by the load, the empty cars come back to the battery through the negative side and are refilled again to complete the circuit. Notice the freight cars are connected end to end and travel at the same speed through all parts of the circuit. Think of the freight cars as current flow. Current is measured in amps and is actually the flow of electrons passing a given point in 1 second. To prevent excessive current from damaging our circuit, we need to install a fuse. Fuses are really protection devices designed to open the circuit when current flow exceeds the rating of the fuse. When a fuse blows, it usually means there's too much current flow caused by too little resistance somewhere in the circuit. A switch allows us to control current flow by turning the load on or off. In this circuit, the load is the factory's light bulb. Loads are devices that use voltage to perform some kind of work, and in this case, the voltage is used to light the bulb. The load is built into the circuit to limit or control current flow. And when a load consumes or uses voltage, we call that a voltage drop. The last and final piece of our circuit is the ground. The ground is the current flow path going back to the negative battery terminal, making the circuit complete. Current cannot flow unless we have a complete circuit and voltage. The blue section of our circuit represents the body chassis and battery ground cable. Remember that the freight cars come back to the battery for more voltage. When a circuit is operating, current flows back to the battery through the ground side. We see examples of what electricity does all around us, from lighting lamps to operating electric motors. Yet most of us haven't spent much time thinking about what electricity is. In basic terms, electricity is energy. The electrical energy that powers lamps and motors is the result of energy that is released as one electron leaves its orbit around the nucleus of an atom and moves into an orbit around the nucleus of another atom. In order to have a continuous flow of electricity, three things must be present. There must be an excess of electrons in one place, there must be a lack of electrons in another place, and there must be a path between the two. An electrical power source can be either chemical, as a storage battery in a car is, or magnetic, as the alternator on a vehicle is. An electrical power source provides for a more positive charge to allow for a continuous flow of electricity. It supplies an excess of free electrons in one place and a lack of electrons in another. In a battery, a chemical reaction causes a lack of electrons at the positive terminal and an excess of electrons at the negative terminal. This electrical imbalance causes the electrons to move out of the negative terminal and seek a path to the positive terminal to get to the protons of the positively charged atoms. The paths that the electrons travel through are the wires that comprise the individual circuits of the automobile wiring harness. For an electrical path to be conducive to electron flow, it must be made of a material that is comprised of atoms with easily moved free electrons. Materials with easily moved free electrons are called conductors. Most conductors have fewer than 3 free electrons in the outer shell or orbit. Gold, silver, and copper all have 1 free electron in the outer orbit and make excellent conductors of electricity. Semiconductors all have 4 free electrons in their outer shell and are used extensively in automotive applications because of their electron stability. Examples of semiconductors are silicon and germanium. Insulators are made from atoms that have a high resistance to electrical flow, where the molecules or combinations of atoms are tightly bound and are characterized by the high number of electrons on the outer shell that are extremely difficult to move out of their orbits. Examples of good insulators are plastics, rubber, and glass. The path for electron flow in an automotive circuit then should be through a good conductor, such as a copper wire. And a material such as plastic or rubber should insulate the path to prevent the electrons from leaving that path and seeking an alternative path to the attraction of the positively charged atoms. In order for the electrons to flow, a pressure must push the electrons through the path that completes a circuit. The pressure in an automotive electrical system is called electromotive force, or EMF. Electromotive force, or voltage, is the measurement of the pressure at a point in the circuit where there is an excess of free electrons to a point in the circuit where there is a shortage of free electrons. In essence, the measurement of voltage is the measurement of the pressure differential or the potential to move free electrons through any point in a circuit. One of the important concepts in understanding electricity is magnetism. Magnetism is an invisible force that can repel like things or attract opposite things. Magnetism occurs naturally in some compounds. We can also create a magnetic field by moving electrons through a path, such as a wire. In a magnetic field, the magnetic force lines are organized around the poles. There is a natural force of attraction between two unlike poles, and natural forces of repulsion between two like poles. A conductor that has a current passing through it develops a magnetic field. The direction of the magnetic force lines of the magnetic field depends on the direction of the current flowing through the conductor. If two conductors carrying current in the same direction are placed next to each other, their magnetic fields will combine. If current is passed through a conductor that is formed in a loop, a weak magnet with a north and south pole is created. The strength of the field around that coil may be increased by adding additional loops or by increasing the current flow through the coil or coils. If a soft iron bar or core is placed inside the coil, the magnetic field is greatly increased as the iron bar has less resistance to the flow of the magnetic force than air. An electromagnet, then, is the use of an iron core surrounded by a coil of wire that carries current. The product of an electromagnet is a magnetic field that is much stronger than the field created by passing current through a simple loop of wire. Magnetism and electricity are interrelated. One can be used to produce the other. Induction is the transfer of energy from one object to another without the objects physically touching each other. If a conductor is passed between the poles of a permanent magnet fast enough to cut the magnetic field, a pressure is created that causes current flow in the conductor. When the direction of motion of the conductor is changed, the direction of current flow through the conductor is also changed. Passing a conductor in, then out, and then back through a magnetic field results in an alternating current that cycles from positive to negative to positive, and so on as the conductor is passed between the magnetic poles. The term electrical current is used to describe the movement or flow of electricity. The greater the number of electrons flowing past a given point in a given period of time, the more current a circuit has. The ampere is the measurement of current based on the flow of 6.28 billion electrons moving past a given point in 1 second. Resistance is defined as any force or substance that restricts or opposes the flow of current in a circuit. In every atom, the electrons resist being moved out of their orbits. The amount of resistance of the electrons to being moved depends on the structure of the individual atom. Conductors, as we saw earlier, have little resistance to the movement of their free electrons from their loosely held orbits. Other substances have a greater resistance to the movement of the electrons on their outer shell as the electrons are more tightly held to the nucleus. As current runs into resistance, more energy is required to move the electrons along the path. The rate of the current flow is reduced because some of the electrical energy is used up as heat. The resistance to current flow that produces heat can be measured to determine the amount of resistance. A unit of measured resistance is called an ohm. To this point, we have looked at electricity in terms of the electron flow theory that suggests that since electrons are negatively charged, free electrons move from the negative, or surplus side of the circuit towards an area having less free electrons, or the positive side of the circuit. Most automotive repair literature describes the flow of current using the conventional flow theory. The conventional flow theory states that the current flows from the side of the most positive potential to the side of the least positive potential. In automotive circuits, this means that the positive terminal, or the terminal with the greatest positive potential, is the source of the flow, and the negative terminal, or terminal with the least positive potential, receives the flow. Automotive wiring diagrams show the flow in a circuit from positive to negative. In scientific terms, both theories are consistent and describe the movement of the electrons in a circuit, with the electrons moving towards positively charged atoms in areas with the least positive potential. The relationships between voltage, current, and resistance in an electrical circuit was defined by George Ohm and is known as Ohm's law. Simply stated, Ohm's law says that the current in an electrical circuit is inversely proportional to the resistance of the circuit and directly proportional to the voltage. The amount of current flow in a circuit is determined by the voltage that causes the current flow. As voltage increases, current flow increases, and as voltage decreases, current flow decreases. And the resistance that acts to restrict current flow. As resistance increases, current flow decreases, and as resistance decreases, current flow increases. A change in resistance, either up or down, will cause an equal and opposite change in current flow. The pressure to cause current flow in an automotive system in a fully charged battery is 12.6 volts. When resistance remains constant, any change in voltage will directly affect the current flow in a circuit. If voltage increases, current flow increases, as there is more pressure to move the free electrons. If voltage decreases, current flow decreases, as there is less pressure available to move the free electrons. So when resistance is constant, the change in voltage results in an equal change in current flow. In any electrical circuit, voltage, current, and resistance work together as a mathematical trio. 1 volt of electrical pressure or electromotive force pushing the electrons through 1 ohm of resistance will result in a current flow of 1 ampere. The relationships expressed in Ohm's law are often shown in a circle where E represents electromotive force or voltage, I represents the intensity or amperage, and R represents resistance or ohms. As long as you know the basics of Ohm's law, that voltage equals amps times ohms, you can use the circle to determine the mathematical equations to calculate the values in an electrical circuit. If you know the values of 2 of the 3 variables in a circuit, you can calculate the third using the Ohm's law circle. By simply covering the portion of the circle that you want to find a value for, you can find the equation for calculating that value. For example, if you know the amperage and the resistance of a circuit, you can calculate the voltage. If you want to find the voltage in a circuit, cover the E, and the formula to solve for voltage is shown as E equals I times R. To do the math, let's say you have a current flow of 2 amps and a resistance of 6 ohms. Using the equation, the missing variable voltage is equal to 2 times 6. The electromotive force, or voltage, in the circuit is therefore 12 volts. Similarly, if you know the voltage and the resistance, you can cover the I and get the formula I equals E divided by R. To do the math, if you know you have 12 volts in a circuit and you have a resistance of 4 ohms, you can divide the 12 volts by the 4 ohms and you'll know the current flow is 3 amps. And if you know the voltage and the current flow, you can determine the amount of resistance in a circuit by covering the R and deriving the formula R equals E divided by I. To do the math, if you know you have 12 volts in the circuit and the current flow is 4 amps, then by dividing the 12 volts by 4 amps, you will calculate the resistance of the circuit to be 3 ohms. In all fairness, automotive technicians rarely spend time calculating the values in automotive circuits during their diagnosis. However, this does not mean that they ignore Ohm's law. Exactly the opposite is true, as they use the relationships expressed in Ohm's law to tell if a circuit is operating properly. Because all circuits are built with a specific resistance value and applied voltage, the current flow can be calculated as a specific amperage. Any unwanted change in either resistance or voltage will cause current to change. Your ability to accurately measure voltage, resistance, and current will help you detect any circuit malfunction. Increasing resistance in a circuit through loose connections or corrosion will cause a reduced current flow. Decreasing resistance in a circuit by providing an alternate path to ground will result in an increased flow that will melt a fuse or trip a circuit breaker. Understanding Ohm's law and the relationship of current flow to resistance is one of the most important tools a diagnostic technician has in troubleshooting electrical systems. In this video, we've looked at the basics of electricity, how an automotive circuit operates, and the relationships expressed by Ohm's law. In the next videos, we'll look at automotive circuits, wiring diagrams, and diagnosing automotive electrical circuits. Thanks for watching.